All right, gang, chapter 4 is on routing and switching concepts. We're going to start talking about routing concepts, initial configurations in a router, some routing decisions, and then we'll talk about basic router operation. So I know this is a bit of a recap, but you all know what a router does. It routes. It routes between multiple directly connected networks. We'll talk about the primary functions of a router, how routers use information and data packs to make forwarding decisions. We'll explain encapsulation and decapsulation. They say de-encapsulation, but I just honestly don't like that word. I've said decapsulation forever, and I'm going to continue. But so you'll know, Cisco likes to call it encapsulation and de-encapsulation. We'll compare the ways that a router builds a routing table. We'll explain routing table entries, and we'll talk about how it builds a routing table for directly connected networks. Finally, we'll talk about static and dynamic routing and the differences in those two. So here are just some basic characteristics that networks have. Based on how they're built, topology, speed, cost becomes a factor in all of these. Security, availability, scalability, and reliability. Ultimately, with a network, it's kind of like buying a car. The more you spend, the more features you can get. You just have to decide how much money you have and whether you need those things or not. So why routing? That's pretty easy. Routers are responsible for routing of traffic between networks. Without routers, we wouldn't have the internet. We wouldn't have networks that span outside of, just a couple of computers. So essentially, a router is a small little computer. They have their own CPU. They have their own operating system. In our case, iOS. Remember that capital I. I've talked about the capital and lowercase I and the fun with Apple and Cisco. And they have their own storage. They have RAM, they have ROM, they have NVRAM, then they have flash, and some large ones may even have a hard drive. So here is the back of just a router. We've got a couple of auxiliary ports, a console port. This one's got a mini USB as well as a USB port. It's got two LAN interfaces and two 4 GB flash card slots. They all look a little different on the back, but this gives you an idea. It's more common to see these console RJ45s now than the old 9-pin serial, and what you have to do is have a cable that goes into that to go into serial on your computer. So routers can connect multiple networks, and routers have multiple interfaces, each on a different IP network. It's important, since we're talking about routing now, to remember that we're moving from layer 2 up to layer 3. When we talk about routing, we're talking about routing IP traffic now instead of with VLANs where we were talking about layer 2 traffic. So routers use static and dynamic routing protocols to learn about remote networks and build their routing tables. Routers use routing tables to determine the best path to send packets. Routers encapsulate the packet and forward it through the interface indicated in their routing tables. So here we've got just a router. We're going to type show IP route. It's going to say that the gateway of last resort is not set. We'll talk about what that is later. And we see here that I have a network 192.168.1.0 connected to fast Ethernet 00. I've got .2.0 connected to a serial port and .3.0 connected to a serial port. One thing to get in the habit of, because it's used a whole lot in Cisco, is to think back to your Network Plus days about how to notate classes of networks. Remember that a 24 is a default Class C network. So looking at this, 192.168 1.0/24, you should immediately recognize that that is just a Class C. So routed on that network are going to be from .1.1 to .1.254. So there are some different methods to forwarding packets. Process switching is an older packet forwarding mechanism that's still available for Cisco routers. Fast switching is a common one that uses what's called next hop information. And then Cisco uses one called Cisco Express forwarding. And this is another proprietary Cisco thing. Table entries are not packet triggered like fast switching, but are change triggered. Here we've just got another example of a network. They want to point out here that you've got a couple of connections between each of these, and the reason that we'll look at that is coming up here in a minute. So to enable network access, you have to have a default gateway. First of all, the IP address identifies the unique host on a local network. The subnet identifies the network subnet. Remember, so for a /24, if we were to spell that out, you know that would be 255.255.255.0. For simplicity, a lot of the stuff that we're going to talk about are going to be just Class C networks. But remember, you could make this work with different ones based on how you were subnetting. And the default gateway identifies the router a packet is sent to when the destination is not on the same local subnet. For most of you at home that have wireless, your default gateway is probably 192.168.1.1, or if you happen to have Belkin equipment, .2.1. And what that means is when you go to www.yahoo.com on your browser, your local router says this is not an address for me. So I'm going to send it out the default gateway, and I'm going to let it figure out how to route it. So network documentation should include at least the following in a topology diagram: the device name, the interfaces, the IP address and the subnet mask, and the default gateways. So you need to assign each of your hosts an IP address. And there's two ways to do that. You can statically assign them an address where you go to every single computer on the network and give every machine an IP address. Or we can use dynamic host configuration protocol. And this is where we use a server to assign an IP address to everything on that subnet. And you can use a software to do that, or Cisco routers will run DHCP on their own. Generally, I do not personally use the Cisco DHCP stuff. It's glad that it's there if I want it for a small network, but I usually use one of my Microsoft servers to do these things, or if I've got a Linux server, I'm going to have it running as the DNS server and the DHCP server and let it do everything. What's important is that you only have one on each network unless they're specifically configured to do what's called an 80-20 split with two different ones. So here we've got some LED lights on the back, and this is a Cisco 1941. This is a typical small router. With these small ones, one blink and a pause means that the port's operating at 10 megabits. 2 and a pause at 100, 3 and a pause at a gigabit. If it's green, it's typically an active port, and if it's off, the port is typically inactive. So these ENs are basically link lights, if you think about it that way. So console access requires an RJ49 to a DB9 cable, and then some sort of software to emulate console connection on your computer. Common ones, they talk about TeraTerm. HyperTerminal is one that's built into old versions of Windows. I'm truly not sure if it's in Windows 8 or not, but one that I'm a big fan of is PuTTY. PuTTY's free. You can download it off the internet. I like PuTTY because not only can you connect via console cable, but it also has SSH built into it. So I use it a lot to connect to my Linux boxes when I'm wanting to make sure everything's good with them. So we need to enable IP on a switch. And to do that, to be able to use a switch to manage it, you need to have an IP address. On a switch, the management IP address is assigned on a virtual interface. So here, interface VLAN 1, IP address 192.168.10.2. They specified 255.255.255.0. You can do that same command as 192.168.10.2/24. No shutdown to keep it up. Exit and then assign a default gateway. So configuring basic router settings. First of all, name the device. Give it a device so that it's got a different, unique name from all the other routers. How you name it is completely up to you. I would suggest if you're doing this in a truly large network, come up with some common name so you'll know where it is. For example, if we were talking about the BIPSI campus, I would name all of my routers starting with what building they are, and then maybe what floor they're on, and then maybe the room number they're in. So for me, I would maybe have a router named A2_215, which would tell me that this is a router in A building on the second floor in room 215. How you name them really doesn't matter. It's just if you give them names that will make sense to you, it'll be easier for you to find them on a large network if something goes wrong. Provide a configuration banner. The reason for that is because it provides legal notification of unauthorized access. A case went to court several years ago where someone broke into someone's router and got in and changed a bunch of things, and they ended up not going to jail because they said there was no notification provided to them when they logged into the router that told them they couldn't log into it. So you configure that banner now, and the banner basically just needs to say, hey, unauthorized use is prohibited. Once you've done that one little statement, then you've got a legal case if somebody breaks into your system. And of course, once you've done all this, be sure you save your config. And if you know your config is good, you need to copy it from running back into the default so it'll load when you reboot the router. So to be available, a router interface must be configured with an IP and a subnet. It must be activated by the no shutdown command. A serial cable with an end labeled DCE must be configured with the clock rate. And you can optionally give it a description. So now we get to talk about the loveliness that is IP6. And I'll be honest, my knowledge of IP6 is still relatively low. I have just started learning about IP6. But it's something that you might encounter as more and more places move over to supporting IP6. So if you have IP6 capabilities, you need to assign an IP6 address to your router so that it can route IP6 traffic. And to do that, you use the IPv6 space address command. Here you see they did IP6 address 2001 DB8 ACAD and so forth. Just like IP, you need to do a no shutdown command once you've done it. You may also need to put two IP addresses, a global identifier and a local link address. Assuming that you're running IP6 outside of just your local network, you need that global interface identifier in order for it to be able to assign an IP6 address that can actually get out on the network. 6 is something that you guys should take a little bit of time and familiarize yourself with, especially based on when you took the Network Plus class, because we haven't talked a lot about 6. There are plenty of articles on Wikipedia that will give you a brief rundown. And I went to a webinar last semester on IP6. I will post the link for that for y'all up on Blackboard to take a look at. I think there's some good info in there that might help you kind of learn a little bit more about IP6. Other things you may want to do is configure a loopback interface. And a loopback interface is a logical interface that is internal to the router. It is not assigned to a physical port. It is considered a software interface, and it's automatically in an up state. A loopback is useful for testing, and it's important in what's called OSPF, or Open Shortest Path First routing. So show commands are used to verify the operation of an interface. Show IP interfaces brief, for example, will show basic information about your IP interfaces. Show IP route is going to show the routes that are available. And then a show run is going to show your running config. So we can do these same commands with IP6. Show IPv6 interface brief is going to show a summary of IP6. Show IP6 interface, in this case Gigabit Ethernet 00, is going to show specifically IP6 information on that interface. And show IP6 route is going to show that I have IP6 routing. The show command output can be managed using the following command filters. If you do a terminal length and a number, it specifies how many lines to show before it pauses and asks you to hit the button to see more. That is often used to stop it a screen at a time if you're going through and looking for something. So another thing about Cisco routers and switches is that just like with Linux and Unix, they remember the last commands that you've typed. And generally, to go back to those last commands, you can press Control-P or use the up arrow. To go down to ones that are more recent, Control-N or the down arrow. By default, the last 10 commands are used. You can change that in exec mode by putting show history, or show history will show it. The command to change it is, oh, don't get me lying, I'll look it up for y'all. Use the terminal history size, there it is, to increase or decrease the size of the buffer. So a terminal history size 20 will remember the last 20 commands. So here we're actually looking at the encapsulation and decapsulation of packets. And think back to Network 101, where data from, say, a web browser is going to be at layer 7. It's going to go all the way down the OSI model to layer 1 before it's physically transmitted out. Well, all of the internal devices don't necessarily have to take it all the way back up to layer 7. But they've got to go to at least layer 3. At layer 3, they can learn the IP addressing, and they know whether that device is on their own network or needs to be sent on. So here they show 3 routers. They all take the data up to layer 3 to learn the IP address, realize it's not on their network, and send it back down. The third router says, oh, this is connected to me, so it sends it from layer 3 down to 1 where it's transmitted to the actual computer, which will take the data all the way back up to layer 7 to send it out, for that server request. So in that example, PC1 sends the data to packet 2. Because PC2 is on a different network, it will encapsulate the packet and send it to the router on its network. So it sends that data on, and it's sent forward until it reaches the destination. See here, all the layer 3 data is going to be encapsulated into different frames to be sent along the route. So router 3 forwards it to PC2 finally. Excuse me, router 2 forwards it to packet to router 3, which will send it on. And there it is actually forwarding the data. So here is just a little flow chart of how the packet forwarding decision process takes place. Packet arrives on the interface. The router searches the routing table for a match. If it finds a match, then it checks the ARP cache and forwards it to the host on the local subnet. If it determines it's not directly connected, then it's going to go down here. If it's a remote network, it'll encapsulate it and send it out the exit interface. If it's not a remote network and there's no gateway of last resort, it's going to drop the packet. If there is, it will forward it out. So routers route using what's called the best path. And the best path is selected by a routing protocol based on a value or metric it uses to determine the distance to reach a network. Now, I want to make a couple of important notes here for y'all. I use the term distance and cost, but we don't actually mean cost as in money, and distance doesn't necessarily mean the furthest away. What I mean by that is if you have two networks that are connected together, and one, maybe you've got 3 or 4 routers, and one is connected to 2 other routers on a 256K link, but one is connected to a router in Canada that then connects to the same router that was on those 256K links. But those are gigabit links. Even though that's much further distance, data would flow faster, so the distance cost or value for that metric is going to be lower even though it's further physical distance. A best path to a network is the path with the lowest metric. So dynamic routing protocols use their own rules and metrics to build and update routing protocols. One to talk about first is RIP, Routing Information Protocol, based on hop count. Then OSPF, or Open Shortest Path First, is based on cumulative bandwidth from the source to the destination. Then another one is called EIGRP, EIGRP, or Enhanced Interior Gateway Routing Protocol, and it's based off bandwidth, delay, load, and reliability. When a router has 2 or more paths to a destination with equal cost metrics, the router forwards the packets using both paths equally. If you have 2 networks connected to 2 other networks and the paths are the same, then it will send data out, basically load balancing it between the 2 connections. RIP, OSPF, and EIGRP all support equal cost load balancing. If multiple paths to the destination are configured on a router, the path installed in the routing table is the one with the lowest administrative distance. A static route with an AD of 1 is more reliable than an EIGRP discovered route with an AD of 90. This is important to know because this makes it where if you configure static routes, they get priority over routes that the system discovers. In my earlier example about the 256K links, and then one large link that is much faster but goes further, I can configure my routers to say that the administrative cost of the slower link is 1, and the cost of the faster link is higher, to force traffic to use the lower link, the slower link, even though that's not the best path. So a routing table is a file stored in RAM that contains information about the directly connected routes, the remote routes, and the network or next hop associations. Show IP route will show the display the contents of the routing table. Local route interfaces are added to the routing table when an interface is configured. Directly connected interfaces are those that are directly connected. Static routes are those that I've set up. And then dynamic routing protocol are the ones that are added when the network starts figuring out where things are. And they're added to the table with EIGRP or OSPF based on which one I'm using. So here we've got just a network to give you an idea. And it shows here that if I do show IP route on router 1, I see that 10.0.0.0/8 is variably subnetted with 2 subnets and 2 masks. Notice that's a -8 network, so that's a class A, even though there's 2 class C stuck off the side of it. And it knows that that network is available via 209.160, what is that? 209.165.200.226. So by its connection there, it knows it's available. So here is their little example of how to read a routing table. This is a great little slide to remember, and they've color-coded it for you to kind of give you an idea of what you're looking at when you do a show IP route. The first field will tell you how it was learned, and D tells us that's dynamic. The destination network is listed next. The administrative distance is listed next. The metric to reach the network, then via and the next hop. Finally, the time elapsed since the network was discovered, and then at the end, the interface used to get to it. So a newly deployed router without any configuration at all has an empty routing table. An active, configured, directly connected interface will create two routing table entries, a link local, which is an L, and a directly connected, which is C. So that tells me immediately what is directly connected to this network. Here we've got a directly connected interface. We're looking at R1, and when we do show IP route, I see that these are directly connected to the router. Show IPv6 route will show IP6 routing, just like with IP4. Remember, you're just dealing with much larger numbers here and much larger subnets because our default subnets on an IP6 network are 64 and 128. So static routes and default static routes can be implemented after directly connected interfaces are added. Static routes are manually configured. They define an explicit path between two network devices. Static routes must be manually updated if the topology changes. There's the key, because that means that if something changes, I've got to go in and change it. These are not going to update automatically. Their benefits include improved security and control of resources. You configure it with the IP route command, IP route network mask, and then next hop. And then finally, we're going to exit the interface command. A default static route is used when the routing table does not contain a path for a destination network. And to configure that, we do IP route zeros to zeros on the interface that we're going to allow that traffic out. Here we've got an IP route out serial 00, so we've got the gateway of last resort. So that means everything will go out that interface. Here they're just showing it again. So on IP6, we can do the same thing with : 0 via, in this case, the same serial number or the same serial port. So we've got our IP6 networks. We've assigned : 0 to serial 000. So the gateway of last resort is set for all data that's not directly connected to go out that port. So dynamic routing is used by routers to share information about the reachability of remote networks. It performs remote discovery and maintains routing tables. I'm a much bigger fan of dynamic than I am of static, because as your network topology changes, it will update it for you. This is really important if you're like working for an ISP, because you may be dealing with routers you have no control over. So Cisco support a variety of IP4 routing protocols. eGRIP is one we've talked about. OSPF. is intermediate system to intermediate system. And then RIP, while not used so much anymore, RIP was very good. It's just good for smaller networks. So here, show IP route will give me the information. The gateway of last resort is set here. It has an IP, so network 0000 is set to go out this IP, 209.165.200.226. So in talking about IPv6 routing, we have Cisco supporting RIPNG, which is the next generation of RIP, OSPF version 3, which is IP6 capable, eGRIP for IPv6, which is just called eGRIP for IPv6, and then one called MPBGP4, which is Multicast Protocol Border Gateway Protocol. That's your border gateway with multicast and IP6 support. Here we're looking at it, show IPv6 route. This shows that we've got directly connected. That's a link local, another directly connected. And that is sort of a rundown of brief routing. In summary, there are many key structures and performance-related characteristics when discussing networks, but the main ones are topology, speed, cost, security, availability, scalability, and reliability. Cisco routers and switches have many similarities. That's important. We didn't really talk so much about it in VLANs earlier, but you need a router to connect to VLAN, but you can also make a switch act like a router to route data between VLANs. One distinguishing feature between switches and routers is the type of interfaces supported by each. And the main purpose of a router is to connect multiple networks and forward packets from one network to the next. The routing table is the list of networks known by the router. The remote network is a network that can only be reached by forwarding the packet to the next router. Remote networks are added to the routing table in two ways, either by a static route that we add or a dynamic route that's discovered. Static routes do not have as much overhead as dynamic. However, they require more maintenance if the network changes because you have to go in and change them. Dynamic protocols automatically adjust without any intervention from the network admin. They do require more CPU and bigger routers, but like I said, I kind of like them more because you don't have to go in and change everything. Routers make their primary forwarding decisions at layer 3. However, router interfaces participate in 1, 2, and 3. Layer 3 IP packets are encapsulated into layer 2 data link frames that are encoded at layer 1 before they're sent out on the net. Router interfaces participate in layer 2 processes associated with their encapsulation. The example they give is that an Ethernet interface on a router participates in the ARP process just like other hosts do on that LAN. And then IP6 routing is similar, except you're dealing with huge routing tables and some different protocols for those routing tables. And that is a rundown on routing.